and the word is a string with the elements in X. So like English, we have alphabet with 26 alphabet, and any other words can be combined with this alphabet. So we define a free associative monoid on a set X, namely the X stars. It's the set of all words in X. So this is a free monoid. It's including the empty product to represent one, and the multiplications is given by the juxtaposition of words. So what's the free associative algebra? A free associative algebra C angle X with respect to a generic rating set X. It's a free C module with base X stars by defining multiplication as follows. If we have two basis elements and the product is just the concatenation of the corresponding words. So for the associative algebra, we did not have commutative, not just, we just have the associative product, like the concatenations. And we are considered the free associative algebra. It's with a base field K, and it's characteristic free, and this K angle X, it's respect to a generating set X. This X is, as we told before, of an arbitrary K. So an element of K is in the form of finite sum, like this form A. It's a finite sum of an omega and omega multiply omega. This omega is a word in the X stars, and omega is just the coefficient of the words. So, but just I am alert this word. This is the finite sum, because we have another definition for the free power series algebra, which we have the same generating set X, and but the sum is the same form, but we did not have any restrict on the finite sum or infinite sum. So as we can see, the free associative algebra is just a subalgebra of the K algebra of the former series, and so this sum may not be finite. And what is the centralizer of an algebra? Suppose we have a K algebra A and a subset S, and we denoted the centralizers of the set S in A is the all elements who commute with every element of set S. So we said CSA is the centralizer of A. So just the commutative elements commute with X inside S. So here it's a mistake, it's a typo, it's a small s. So usually we just consider the one element set S. So we just simply write it as CSA. So this is a centralizer of one element set S, and we consider the centralizer. So usually we just interested in the so-called non-scalar or non-constant set, non-constant element S, because if S is in the base field K, then everything is commutative with S, right? Because it is like the coefficients, it's commutative with other elements inside this free associative algebra or the algebra of formal series. It's the same case. So there are several famous centralizer theories. The first one is given by Farrokh in 1964. And suppose it says that if A is a non-scalar element inside the K algebra of power series with respect to the set of X. So this X also have at least two elements. And then the centralizer of A is isomorphic to the K algebra of power series in one variable. So the centralizer is a commutative subalgebra of this K algebra. And since we already know that the free-associative algebra is just a subalgebra of the K algebra of power series. So and its centralizer can also be naturally embedded into the centralizer of K algebra power series. So this centralizer is a commutative K subalgebra of K X. So we want more, and this actually is a hypothesis by Kohn and his student G.M. Bergman proved this in his PhD thesis in 1969, that if A is a non-scalar element of the free-associative algebra, then the centralizer is isomorphic to the one-dimensional polynomial algebra. So this is what we want to reprove or use a new method to prove in this talk. And for the original proof by Bergman, he developed some combinatory and evaluation ideas from Kohn, and the proof is somehow not it is somehow not easy to read, but
so what is J? What is J xi xj?
I will explain. J is the Jacobian determinant. So after that, the Shestakov and Lumibaev developed. Actually, they give an analog.
Wenchao, can you comment it a bit more? It's
yes.
GXIXJ. It means that
yes.
df by dxi dj
yes.
by dxj minus df by dx.
To write it. No. Just saying it maybe. It would be better to write it. So formula.
Okay. Yes, because there is no actually all the elements in the polynomial algebra kx1 to xn, it's always commutative. So in this sense, the centralizer is just the whole polynomial algebra. But the Shestakov and the Omipev, they just make an analog to the centralizer. So they define the other things, not define the commutator. So the other centralizers it's just like the commutator is zero. But here we have a Jacobian. Jacobian just said it's the partial f and partial xi, partial g, partial xj minus partial f, partial xj, and partial.
No, we don't see it written.
Okay. Yes. I'm sorry. So
can you chat?
Okay.
Okay. So you can you chat?
Yeah. Okay. I'll try to write it down. Chart. Just like this. Okay. So this means this. Actually, it's like the determinant. It's like this. This is G. So this is the two-dimensional Jacobian, just this J, Xi, Xj, Fng. So they calculate this Jacobian. If this Jacobian is 0, then by this definition, this if we call this the centralizers, then for any non-scalar elements f, we have the centralizer is also isomorphic to kx. But here he just proved the k is characteristic 0, not characteristic 3. So this is the the story. So does it keep clear?
Okay.
Okay. So let's continue. How to? Okay. How to? Okay. Let's continue. So what's more, we can also generalize this centralizer series in other algebra.
Excuse me, there is a question on the chat line
Sorry.
about indices.
Indices. Okay.
Yes, sorry, I was just asking if the indices for the expression of the Jacobian that you wrote down were in the right places, because then you have df dxi times dg dxi minus df dxj minus dg dxj. Do you want the i's together and the j's together?
No, I think no. So no. I with J and J with I. So
Okay, got it. Okay.
Okay. So it's I with J and J as well. Okay. So there are other generalized centralizer theories, and one is it's about the free Poisson algebra. So this algebra, we first have a Lie algebra L, and with some linear basis, L1 to Lk over a few k. So denote that PL is the polynomial algebra on the variables. So we view linear base as variables, L1 to Lk, and then use the Leibniz identity. We can uniquely extend the Lie bracket to the Poisson bracket. So, and this algebra is called the free Poisson algebra. And in 2007, Maklimanov and Umibaev proved that if K is characteristic 0 and F is an non-scalar element inside this free Poisson algebra, then the centralizer is also isomorphic to the one-dimensional polynomial algebra. So, and after that, there is a recent result by Maniskov. He gave a similar result for the free group algebra. So if F is a free group on a X, it's on an X alphabet set, and the centralizer of any non-constant elements in the free group algebra KF is given by this. So either the centralizers of this non-constant element is isomorphic to the rings of Laurent polynomial, it's k, t, and t minus 1. So or else the C is the affine coordinate rings of complements of k points in a proper non-singular curve W over k. So this centralizer theorems we already know, and today we'll give additional proof for the Bergman theory, because it will help us to prove others, like the direct result is actually this free Poisson algebra. So this is let's see. So, but before that, we need some additional tools. So we call it the generic matrix. Since at the original, we won't do the quantization for the free associative algebra directly, but we found some gap. But after we use the generic matrix, we can fix that gap. So what is generic matrix? A generic matrix is a matrix which entries are distinct commutative indeterminants. So it's no longer just a number in some number field, and it can be any other commutative indeterminants. And this, let n be the positive integer. It's an n by n matrix, and suppose we have at least two generic matrix x1 to xs, and with entries, the entries of the matrix are independent central variables, then the K subalgebra of the matrix algebra of Kxi nu is generated by the matrix X nu. X nu is this x1 to xs. It's called the algebra of generic matrix, and usually we will denote it by K into big X1 to xs, or we can use K bracket of X for short. And the algebra of generic matrix, and somehow it's a basic object in study of polynomial identity and invariance theories for the n by n matrix. So there is the canonic homomorphism from the free associative algebra and the algebra of generic matrix. So this pi from kx1 to xs and to kx big x1 to bx x, and from this we can do, if we have u1 to us is n by n matrix with entries, it's a commutative K algebra R, then we can just substitute this mu j to this xj, and thereby we obtain a homomorphism. So from kxi to xns to mnr. So this means that the kernel of this pi, if the element f is inside the kernel of pi, then if and only if it vanished identically on MNR for every commutative K algebra R.
Excuse me, about what the map is. How do you define it?
Actually, we mapped each this indeterminants to a generic matrix. So it's the small xi to the big xi.
No. What xi big xi is? So you say a canonic
is generic matrix. Big xi is generic matrix. So the generator of free associative algebra is sent to corresponding generators.
But what do you mean by corresponding? You say canonical. Canonical means that that it's something quite concrete. Otherwise, you just say.
It means that if you have in category of algebras with fixed set of generator.
Well, okay.
It is what is the generic matrix algebra? Is a free algebra with some set of identities. You can consider free generators of free associative algebras, and there are free matrix whose entries are algebraically independent. This is algebra of generic matrix, and then you free generators of free associative algebra you ascend to generators of generic matrix. This is called its standard notation canonical homomorphism in this science.
Okay.
It's not canonical if you consider as an abstract algebra, because you can list for any automorphism or whatever. But it is canonical in category of algebra with fixed set of generators. No, like ring at polynomial to some factor. Okay.
Okay. So
Did I answer the question?
Okay.
Okay, so it also means that if only if x vanishes identically for all the a matrix, the algebra of matrix M and K. So this K is the base field, and so this gives us any matrix representation of free range A of dimension less than n, corresponding to the bijective to the generic matrix, the matrix representation of generic matrix. So this somehow is so-called canonic homomorphism. And this lemma shows that the algebra of generic matrix is a domain, and its localization coincides with the localization of algebra of generic matrix with traces, and it traces for the positive characteristic is with forms, and it's a skew field, and this fact. The fact the algebraic of generic matrix is a domain and its localization is a skew field was established by a meter. And
how do you so what is algebra with traces?
Yes, we will show that. So
what is it?
Can I answer the question? Suppose you have a generic. Suppose you have algebra with algebra. What is this? Is a structure with multiplication. Yes. You have binary operation multiplication, but algebra with traces. You have also unary operation taking trace of algebra, and the algebra with two operations. Binary multiplication and taking trace such that trace A plus B is trace A plus trace B, trace AB equal trace BA, and next and the and trace commutes with everything is called algebra with trace. You just extend signature of algebra by taking trace. Or you can extend signature to taking determinant or all other characteristic coefficients in Hamilton-Cayley equation. In this situation, we call this algebra as algebra with forms. Did I answer this question?
Yes, sure.
Okay.
Okay. So now it remains to show that the localization coincides with the localization of generic algebra of generic matrix with traces, and we will show that. Consider that the Hamilton-Cayley identity for this MI matrix we have AM minus psi 1 A. This is n minus 1. Sorry, this typo.
So what are we proving?
We are proving that moment. We are proving that the localization coincides with it's the algebra of generic matrix with traces. It's the localization of
so if you localize algebra with trace coincides with algebra, usual algebra without trace.
So their localization coincides. So whether we have with trace or without traces, just prove this. So here we consider the Hamilton-Cayley identity for n by n matrices, and this is a n psi a. Here is a n minus 1. There is a typo inside this, and the psi a is sum of the main minus of a of order k, and consider a polynomial f. It's a polynomial of z and y1 to yn minus 1. And t is a it's independent, and this is multilinear and skew symmetric respect to the first n entries, z and to the y1 to yn, and this somehow depended to other variables t. So we use the vector here because we didn't know the dimension of t, and let z be the xn and yk is the set of y1 to yn minus 1, and we rewrote it as x to n minus 1 to 1. So here we have n entries, and we just get rid one of this xk. So now if we replace this z by xn plus minus 1 to k and psi kx xn minus k inside this polynomial, then we can get 0. So because of the skew symmetric and the Hamilton-Klein identity. So then, on the other hand, this xk combined with yk is just 1 to the n minus 1 for generic matrix x. They are linear independent. So this fx n minus 1 to 1 is non-zero for some f. So we can put this fy1 to yn minus 1 with this form, and then we can have the result for the psi kz with a rational form fx and ykt and fz n minus k by kt. So and this denominant is non-zero, can be chosen as non-zero. So we then express the characteristic coefficient as the fraction of the ordinary polynomials, and this is so-called we just do the localizations. Okay, but what is more important for us is this Amice-Levinsky theory. It's for the PI theory. So for free-exhaustive algebra K x, we already know the commutator is just the commutator bracket xy is xy minus yx, and there are some other analogs for more variables, and they are called generalized commutator, or we can call it a standard polynomials for x1 to xn. So this Sn x1 to xn is defined as this way. So there are summation of x sigma 1 to x sigma n. This sigma is inside the symmetric group, and multiplied with the sign of this sigma. So sigma runs over all the elements of group of permutations. So it's clear that if n is 2, it's just the commutators. So and what's more, Amice and Levinsky shows that if we have A1 to A2n, there are two n's, n by n matrices, then the standard polynomials of this A1 to A2n, S2n is equal to 0. Actually, it also says that this 2n is the least number of the for the n by n matrices. So Amice and Levinsky just shows that this 2n is exactly have is exactly fixed this
And
polynomial.
why is it the smallest one?
What?
Why is it the smallest one?
It's there is a
Which
proof of
proof?
there is
Yes.
there is a classical theorem which is not so trivial but not extremely difficult.
So
Okay.
yeah,
There is a way, or there is I can refer to some classical book. There is a proof of that, but this proof is not so trivial. It's not extremely difficult, but this is somehow maybe 3 pages proof, something like that. In fact, it is minimal one.
yes, and so this somehow we will use in our proof for the minimum of 2n. So we just, and what's more, we can prove this some properties of the algebra of generic matrix. So let's let this case bracket of x be the algebra of generic matrix with traces. So as we showed before, if R is center and let K be the algebraic closure of the field of fractions of this R, then the minimal polynomials of any elements inside the K bracket of X is irreducible over R, and in particular it's diagonalizable. So this is somehow very important to our proof, since the calculation becomes simple. And we also shows that all the eigenvalues lambda I are the roots of the minimum polynomial of A with some multiplicities. And so this means that the characteristic polynomial of A is just the power of the minimal polynomial. And if we choose a big enough P instead of the n times n matrices, then the minimal polynomial will coincide with this characteristic polynomial. So here we just saying that if A is a non-scalar generic matrix of K bracket of X, and the minimal polynomials coincide with this characteristic polynomial, and also A is, it can be diagonalizable over the K, the algebraic closure of the field of fraction of the central R. And this is helpful. When this n is also viewed as a prime, if then all eigenvalues are pairwise different. And we also consider the other generic matrix, which is commutative with A. So if there is another generic matrix which with the same eigenvectors, then it's also can be diagonalizable. And this is not shown here, but here we have another result. So if the generic matrix is with the same eigenvectors, then vector as x the non-scalar elements, which is diagonalizable, will commute with A. So this set of all the generic matrix commuting with A are diagonalizable with A. So, and they have the same eigenvector basis as A. And And then we can also consider the relations between the free associative algebra and the algebra of generic matrix. So if we consider two commutative elements and the non-scalar elements of the free associative algebra, and suppose they are commutative, but the rank is at least 2. It means that they are algebraically independent. So we won't use the proof with contradictions, and we will show that the subalgebra of n by n generic matrix generated by the reduction of f and g will also have rank 2 for big enough n or p. So assume that this f and g is a commutative algebra generated by the f and g, and this f and g is just the non-scalar elements of free associative algebra, and suppose it's rank 2. So we denoted f bar and g bar as the reduction to the algebra of generic matrix, and with n by n matrix. So the rank of k f bar and g bar must less or equal than 2. So suppose the rank of 1, the rank is 1, so we will make a contradiction. So if for any other elements inside this subalgebra, I mean the A and B, there is a minimal polynomial, it's px1. Since we already used the rank is 1, so there must be a minimal polynomial px1. It's inside the kxy. So suppose it's degree n, and such that after reduction we have pa bar and b bar is 0. So since the algebraic of generic matrix is a domain, and by the lemma 6, it's actually the it's a domain, and we have the localization is skew field. So what we have, and on the other hand, by the Amiza and Levinsky theory, so there is no polynomial with degree less than 2n. So such that this PA bar B bar is 0. So if we choose this n big enough, which is bigger than the floor of n over 2, and also we can choose a prime, and which will contradict with the Amiza and Levinsky theory. So we just need to choose a big enough n. Then we can show that if there is a commutative subalgebra which are algebraically dependent or rank 2 in the free associative algebra, then we also have a subalgebra of generic matrix which also have a rank 2 for big enough big enough n, means n by n matrices. So this gives us a relations between the original free associative algebra and the generic matrix. This means that if we can prove something in the generic matrix, then we can get the same contradiction for the free associative algebra. So now it becomes our main tool, the quantization. So what is the deformation quantization? So suppose K is an field and A is a unitary K algebra. So we denoted the K H bar is the ring of formal power series in one determinant. So we just introduce a new indeterminate H. So this is somehow a smaller indeterminate, and we will show it after we we do some reduction or modular h bar square, something like that, and we will show that. So, and the h bar is the kh bar's modular of formal power series with coefficient in A. So what is formal deformation? A formal deformation or the star product of A is an associative H-adic continuous H bar bilinear product. So this star product is map from it's a new product from AH to H. So satisfy the following rules on A. So F stars with G is the bilinear. This Bn are all bilinear operators of F and G. So we can B0, it's actually F times G. And we also have this form from n to 1 to infinite. So this Bn is just bilinear operators. And we will show that there is a okay. So we will show, sorry. There is natural group acting on this star product. So the group consists of the automorphisms of AH considered as a KH module of the following form. So if we send F to F plus some summation of dm, the di is differential linear operators of F and with h bar n. So then we can also send in fn hn to fn hn multiplied with some dm fm hn minus. So here it's also a typo, is dn fm here. So this dh is 1 plus the summation of dm hm. It's an automorphism, and it defines an equivalence and acting on the set of star products as follows. So if there's two star products and the f h bar with star prime b bar, it's some combination of this. So actually we have we don't have exactly uniquely star products, but somehow they are equivalent for this equivalence class. So sorry, I can't do it. So there's lemma about this formal deformation. If the this is a associative star product of the multiplication of associative and commutative K algebra A, and for any two elements of A, so we put the Poisson bracket as the first bilinear operator B1FG minus B1GF. So actually this can be shows that like this way. So we just, so here we denoted U star V minus V star.
So you are going very quickly. So there is an important.
Yes, I will be back because I didn't show it here. So maybe after that. So the map, the bracket map is a Poisson bracket. We can verify it and on A, and it's a K-linear map such that the bracket is a Lie bracket and also satisfies a Leibniz rule. And the bracket is also is dependent only on the equivalence of the equivalent class of star product. So we just consider the equivalence class of star products. So what we used is so-called conservation deformation quantization. Concise shows that if we have a smooth manifold M and A is the smooth function on M, and there is a natural isomorphism between the equivalent class of deformations, means this formal deformations of the Poisson structures on M and the equivalent classes of smooth deformation of the associative algebra A. So in particular, so any Poisson bracket on A comes up from the canonic defined star products. So it means that if we have canonic defined star products, then we will have a Poisson bracket on M, and on the so this is useful in our proof because since our subalgebra, we suppose our subalgebra is generated by two commutative elements f and g, and if we can we first can reduct it reduction to the generic matrix, then consider the deformations, then we will get a Poisson bracket, and after some calculation we will show some contradiction. So we just denote it by the u star v minus v star u for short at this commutator. So we call star commutator here, and this just shows that the Poisson bracket uv is just 1 over h, the uv star product minus the uv commutator. Actually we used our two commutative algebra. This is 0. So since we already know there's the generic matrix, which is the non-scalar. If A is a non-scalar element for the generic matrix, then A is diagonalizable over some extension, finite extension. Then we also shows that after quantization, the A hat can be also diagonalizable with some finite extension. So this is important. You can show the proof. So suppose we have this form. A hat it's equivalent to A0 plus some h bar A1, and here A0, since it's already diagonal. After diagonal, since the A is diagonalizable for the generic matrix, so then we can just cancel out this A1, and which means that A hat can be also diagonalizable. So suppose A0 is a diagonal generic matrix with distinct eigenvalues, which we stated before, and we want to show that there exists an invertible generic matrix P such that P minus 1 is diagonal.
Just can you go to previous slide?
This one?
Wenchao, can you get to previous slide?
This
Just
one?
before, one slide before.
Here?
Previous slide.
Period.
Previous slide. Okay.
This.
I want to say this. I want to mention UV to
Next one?
No, previous.
Here?
Previous. Next.
Not
about okay, next.
Next. This one?
Where you have a commutator, star commutator. Can you show?
Here. Okay. square commutator.
Okay, next. Not previous. Okay, here we are. I want to mention, then you have star commutator and this relation with star commutator and H.
Mhm.
Okay, then continue. Okay. Formula
Yeah.
6, I want to. Okay.
Okay. This one. Okay. Yes, this it's the equivalent H. Okay. So let's be back to our proof, and now we consider the quantization. So we may assume that P hat is I plus some H bar T, and junction inverse P hat minus 1 is I minus H bar T. If we modulo H bar 2, because this modulo H bar 2 it's the identity matrix. So then we have this one, and the first part is A0, and the other parts we have H bar. There is a commutator of T and A0 plus A1 modulo H bar 2. So we just need to solve this. We want this to be 0 for the diagonalize. So just to show the commutator is minus A1, we just show which T we want to use. And since A0 is diagonal, and we can write it as a diagonal form, lambda 1 to lambda n, and T is Tij, and A1 is Aij, and we have this one, because this is, and hence this T can be calculated at this form. So if we choose T in this form, since they are pairwise different, so this we don't need to worry about this. So far, we can determine the H bar term of the matrix A bar, which shows that it is diagonalized when we modulo H bar 2, and then we can also assume that a new A hat to A0 plus H bar 2 A2 modulo H bar 3, and continue to cancel the H bar 2 term, which is similar. And we also have P2 minus 1, and then it's similar forms for that, and we can choose this T2 with this form. So this process can be do, but actually we just need to the modular H2 bar, since the quantization idea, we can use some reduction for several powers. So this list that result it can be diagonalized over the extension kxi mu, and with some 1 over lambda I minus lambda j. So here comes our main theory about the this one. So if A and B, they are two commutative generic matrix, and it's non-scalar in the H generic matrix kx1 to xx with rank 2. So if they are rank 2, so let A hat and B hat be the quantized image, and which is sending multiplication to the star product, I mean and of AB respectively. If we consider the lifting to the quantization, then the A hat B hat do not commute. And what's more, we can calculate the H bar 1 over H bar A hat B hat stars. It's a diagonalized form modulo H, and H each turn of the diagonal is non-zero, and lambda I and mu I are eigenvalues or the weights of A and B. So we already showed that this A and B can be both diagonalized over some finite extensions. Then consider the result of diagonalized with quantization form. Then we can write it at this form with modulo H2. So A hat its first it's diagonalized, and then it's H bar with some lambda I to lambda delta I to delta 1 to delta n. B is for mu1 to mu1 plus with a diagonal form. And we can calculate the star commutators A and B, which is also the Poisson bracket as we defined before. And here we have a diagonalized form with the Poisson bracket of their eigenvalues, and plus some this lambda. It's just the lambda I to the diagonal matrices with some zero diagonal form, and we can show that this for matrices, the result of four matrices, they all have empty diagonals except the first term, and the first term is the Poisson bracket of the eigenvalue, since they are pairwise difference, so it's non-zero. So it means that the
Sorry, Wenchao. This is empty. The second, this is empty on the diagonal, and the third terms are divisible by h.
yes. It's
Last string is divisible by h, and the second string is empty in the diagonal.
Okay. So so last term.
This is empty in diagonal.
Yes. Actually, I just.
But this is divisible by h.
Yes. I already removed. Yes, I already removed something is divisible by h. So I think it's okay. So this shows the Poisson bracket or the star bracket star commutator is non-zero. But on the other hand, so we consider before, if we have a commutative subalgebra of rank 2 generated by A and B, which is a non-scalar elements of the free algebra, then we consider the reduction to the algebra of generic matrix as big N and big B as pi N and pi B. So since A are commutative, and so this shows that the pi of the commutator of AB is also 0, and after quantization it should be 0 as well. So this will lead in a contradiction to what we just showed, that the star commutator is non-zero. So this means that there is no commutative subalgebra of rank greater or equal than 2 in the free associative algebra. So this part we show the key results of the Bergman centralized theory, that if we just show the equivalence of the commutator 0 and algebraic independent. So if its commutator is 0, then it's algebraic dependent. So but actually it's not enough, since we must prove that the centralizer is also integrally closed in order to complete the proof. In fact, we already showed that it can be embedded into the polynomial range of one determinant. So if C is also integrally closed, then it can be shows that it's isomorphic to the polynomial ring of one indeterminate. So this is by the Lewis theory. So, and because of the time lack of time, so
No, you don't have lack of time. So far we are up to noon. It
1
means
hour.
up to
Yes, yes.
5 in Beijing.
Okay.
Half an hour.
Okay. So we have another part for to show this integral closed, and let's show this in this way. Sorry. Okay. So, but we need some more things about the invariant theory of the matrices. So let's have a look. So here we just saying something about the algebra with traces. So let's shows that it's integral closed. Okay.
Can I comment this? Maybe,
yes, please.
Maybe I will say about quantization. First of all, I want to say that there is very nice papers. There is two nice papers of Pavel Kolesnikov who made some reproof of the Makar-Limanov algebraic skew field construction. And he had the papers of the notions of the algebraically closed skew field. In fact, he resolved some system of equation and he works with Moyal-Weyl product. In fact, he used very close consideration as Kontsevich quantization theorem in some other the content. By the content, I mean that content of the classical result construction of algebraically closed skew field. Because in fact, he interpreted the elements of ring somehow as a differential operators, and via some formal series, he resolves equations. There is and how to proceed, there is two papers of the Pavel Kolesnikov. That's what I want to mention, that somebody consider mainstreams like just for mainstream, but this mainstream and quantization issues allows to resolve question in classical mathematics, which is things important. And then another thing, I had the paper with Kontsevich about Jacobian conjecture implies Dixmier conjecture. Dixmier conjecture says that any endomorphism of Weyl algebra is automorphism. I can sometimes make a talk about this.
Okay.
If you have slots sometime. No, according to your convenience, that the Jacobian conjecture implies Dixmier, I can prepare and all of the stuff, but this is a part of project. There is reference we made monography of usage of some quantum ideas to classical algebra. This is one stuff, Bergman stuff. And the second part of the paper is a bit complicated. It's about algebraically about algebra of generic matrices, and this okay, and that I wanted to say. And the next issue is about, you said about the lecture about of this guy. I did not listen, but I would be happy to listen, and then I can react on your question.
Okay. Actually, there is a course of lectures about various things in algebraic geometry and on commutative algebra theory, and he's talking about invariance, and Borchers is talking about invariant theory and some theorems like Hilbert's theorem on finite extensions. And he's asking about various resolutions and syzygies of various matrices, various, rings. And he's asking, well, assume we have just n by n ring, and so what sort of relations can we have? So we could definitely have Hamilton, Kelly, but what else can we have? Okay, thank you very much. Well, considering your talk, I think we can fix it for somewhere in March. So if you don't mind, Sanjan will contact you.
Okay.
Because all of this is pretty different ideas, and it's unreasonable to discuss now any ideas except quantizations, because invariant idea, and also meanwhile Wenchao and I will listen Borges, and then we will react, and then we answer your question. It's pretty interesting for me. Maybe we even can write additional paper, because maybe we have technique to resolve question. Who knows?
Okay, so just type Borchert's YouTube commutative algebras, and I think one of those lectures will be about that. I don't remember the number of the lecture, but he's talking just about that. Okay, thank you very much.
Okay.
Are there any further questions, remarks, comments?
Let me say about the how works how Jacobian conjecture implies Dick square conjecture. If you consider VL algebra differential operators modulo prime, modulo p, then it has a center generated by x to the p and y to and d by dx to the p. No, because x to the p commutes with d by dx. But the center has a structure of Poisson brackets. X to the p, you consider commutator with d by dx to the p. Result divide by p and send back to characteristic p. Lift x to the p to characteristic 0 somehow. Lift d by dx to the p to characteristic 0. Then commute, divide result by p, and send back. And this is well-defined operation. Prime number plays a role of Planck constant. And
Okay. So
this ideology. I want to say that this ideology really interesting in classical mathematics formally without any quantization consideration.
Okay, it's great.
Okay.
Well, okay. Okay, so thank you very much. So we have got a lot of materials, and so we are looking forward to your further talks. So are there any questions?
And thank you for your output for both.
Thank you.
Okay, thank you. So can you
Yes.
also add me into your mail list of the seminar?
Yes, sure. Yes, sure. Please add. So please add the speaker to our seminar mail.